Hello, welcome everyone. So this is our next lecture as a part of our IMSC 60 colloquium series, and it's a pleasure to have Ayan Mukhopadhyay with us. So Ayan did his PhD from HRI with Professor Rajesh Gopakumar, and then he had postdoc positions in several places in Europe. And then he was a prestigious Lise Meitner Fellow at Vienna, the Institute of Physics. And then he joined in IIT Madras in 2018. So Ayan has very broad interests. So he started working in string theory, then he went into semi-holographic models of QCD or gauge theories, where one understands many qualitative aspects of non-equilibrium gauge theories, and he was one of the first proponents of it. And of course now he's working on quantum computing and the interface with gravity, and he will tell us more about black holes and quantum channels today. So Ayan, is a great pleasure to have you.
Thank you very much, Shantan, for this rather kind introduction, and it's certainly a very overwhelming moment for me to be invited to give this Golden Jubilee celebration, or one of the Golden Jubilee celebration talks. It's really a great honor for me. Thank you very much, and I'm quite overwhelmed. So, so my talk would be about this recent progress on black holes and the information loss paradoxes, and I think probably it's one of the most deepest advances in theoretical physics in recent times. And I would say that it has also a lot to do with many other branches of physics. It's not only going to be important to understand quantum gravity, but also it could create and set new paradigms for understanding quantum systems in general, and also understanding limits of quantum computations. So I think it touches upon a lot of questions, and a lot of developments in theoretical physics will come from it. So it's really a gold mine of theoretical physics, where an enormous progress, and I mean, in fact, things that we cannot even imagine now can come from here. So let me convince you, I will be happy if my colloquium talk convinces you that is a rather important advances have been made recently, and this is a direction that can lead to really a lot of unexpected and perhaps revolutionary advances in theoretical physics. Okay, the plan of the talk is as follows. So I will cover first the black hole paradoxes in a nutshell, and I will rather have nothing new insight to offer, but it will be just a quick summary of the old things. And then I will again go to I will just set up the language, because this colloquium is supposed to be to the whole institute, and I would rather give some basic definitions of this quantum information things that I would be using. And then I will come to the main ingredients that has led to this advances in understanding of our black holes, is this quantum information theory of holographic spacetime, where you understand the holographic principle of quantum gravity in terms of a quantum information theory. And then we will see how these older things have led to the new, just 2 years ago, some new way to reproduce the page curve, which leads to in principle, a better understanding of how the information paradox is resolved. So, but it's not resolved yet. I should emphasize that. There are many important questions remain. And I will try to then say what are the many other features and paradoxes that we don't understand yet. And we will, in the last part of the talk, I will talk about what we are doing, and we will highlight some microstate models, and also I will talk about the applications and show that, or try to convince you that understanding the physics of black hole microstates will have applications even outside of this quantum gravity, even to understand strange metals or many complex quantum materials we would need, or even to understand the structure of proton. All this might be important for us, and in what sense. And then I will end with some concluding remarks of things that I couldn't touch or just barely touch. Okay, this So a lot of the talk would be based on the review that I got a chance to write. Actually, this review is part of a collection of articles which reviews many recent progresses in holography. And so I'm the guest editor of this volume, and I got invited to be the guest editor. So it is already, all the 7 articles are published, and this article is simply one of the 7 articles. So I invite you to read it. And most of the pictures that I will be taking will be from this article, but many of the pictures are from other papers. So so if I don't mention explicitly, it's either one of the picture that Tanay has drawn or a picture that is from other articles which appears in the review. So with this apologies, so I apologize if I'm not able to always say the source of the picture. And then for the microstate models, this is our work in 2020, 2 years ago, but the main things are, I will just simply sketch that what there has been progress on this. And then the third paper that I will be talking about in the context of strange metals is something that will come out soon, hopefully by the end of, or the beginning of June, or by the end of this month, hopefully. And then there'll be some other works also I'll briefly mention. So now I start with this is a summary of the black hole paradoxes. There's nothing new, as I said, I could offer here. It's just really a summary, probably a bad summary. So, popular science level sometimes. So this is the Hawking's famous paradox which started it all. So Hawking did a computation which was first, he couldn't believe himself, but later he convinced himself and convinced others. And that a black hole classically only absorbs everything, but quantum mechanically the vacuum fluctuations around the horizon of a black hole would imply that the black hole emits as a thermal black body. And essentially the temperature of the black hole, of the radiation, is related to the surface gravity at the horizon, which should be uniform. That is the 0th law of black hole mechanics. Just classical black holes, once they settle down, should have a uniform surface gravity. And that's sort of the 0th law of thermodynamics. And this temperature is then a uniform temperature. And actually, so the origin of this result can be understood in very briefly through this cartoon, is that if you look at modes of the fields outside the horizon, then you could do a Euclidean continuation and understand how to reproduce the Euclidean correlation functions of this fields. And the Euclidean continuation of the black hole geometry is actually something like this, looks like a cigar. And the important thing is that there is a time, the time has a periodicity. And you have to have the right periodicity of time such that you don't have any conical singularity at the horizon. And so the horizon looks like a plane, actually. And this time becomes this theta, what we call this angular direction, with a particular periodicity. And this periodicity is essentially this temperature, because quantum mechanically a periodic time will give you a temperature. And then the question that arose and has still remained is how is unitarity restored? Because a black hole, you can form a black hole by throwing in some matter. It will be in a complex quantum state, and then the black hole gets formed and starts emitting radiation. But this radiation has only one parameter, the temperature, and it loses information of all the quantum properties of the state is gone, and information of that is gone, and we have only information of that total amount of energy of the matter that formed the black hole. So Page actually gave another version of this paradox, which actually in 1994, I think, and so he formulated this paradox in a different way, which is often called the Page curve. So he was saying that let black hole be like burning coal, and suppose we could think of black hole, like we can understand black hole as some like ordinary matter, like ordinary black body, then you can think that in this way, that if you look at the full space, Hilbert space of the coal and the radiation, then you can define something called a page time. And the page time is essentially the time when the coarse-grained entropy of the black hole is exactly that of the radiation. So the entropy is essentially a measure of our ignorance, how much ignorance we have of the system. And this is what is called entanglement entropy in the quantum case. So if you look at the entropy of the black hole, that should go down, and because simply most of it is being emitted as radiation, and the radiation entropy of the radiation will go up until they converge. And the coarse-grained entropy basically means the follows, that you do some very simple measurements on the system, and then you try to represent this the result of these measurements through some density matrix or through some macroscopic state, and you take that macroscopic state which has the maximum entropy, and you call that the coarse-grained entropy. So basically, it is the entropy of the state of the macroscopic state that reproduces simple measurements that you do, and which has maximum entropy. So that's the coarse-grained entropy. But then if you start from a typical state, what you can show that exactly at the page time when the radiation and the black hole have equal coarse-grained entropy, this curve should turn around. Unlike the Hawking calculation, which goes up, the entropy of the radiation should go down and eventually become zero. And in fact, that means that the black hole and radiation together, of course, is always a pure state, but the entropy becomes, but the entropy starts, the information about what is inside the black hole or how the black hole was formed will start coming out, and essentially the radiation on its own will become a pure state. So this is something that you can reproduce. If you are burning coal, you should be able to reproduce this thing from effective field theory. And there is no controversy how this page curve can be reproduced from a burning coal. However, we don't understand how effective field theory can reproduce this for a black hole. So how effective field theory actually reproduces this, that is something we don't understand. And that is the job of a quantum gravity model, to make you understand that. So the area of the black hole then turns out to behave like an entropy. The entropy of the black hole is captured by the area. So this was something that was kind of controversial, or kind of was a surprise earlier. Even Hawking didn't believe it. But the result actually came from Hawking's theorem that the area of a black hole horizon area of event horizon of the black hole can only increase. And this is the so-called the second law of black hole thermodynamics. And this has now been verified in black hole mergers. So if you take a 30 solar mass black hole and a 40 solar mass black hole, the area of the event horizon of a black hole is proportional to the mass square, because the Schwarzschild radius is proportional to the mass. And so 30 square plus 40 square is 50 square. So the black hole merger, the final black hole that is produced through the merger, should at least have a solar mass of 50, cannot have anything less than that. And this is all black hole mergers satisfy this. And so in fact, if Hawking would have been alive, he could have won a Nobel Prize together with Penrose. What Bekenstein noted that if you want to protect the second law of thermodynamics, so if you throw some kind of matchbox inside the black hole, the black hole mass will increase, and whereas you lose entropy because you've thrown something inside the black hole, you can account for it. But however, you say that the black hole has precisely this entropy, then you can restore the second law. And this essentially means that you're measuring the area of the black hole horizon in terms of Planck unit and a quarter of that area. So Bekenstein proposed this formula, and this is called the Bekenstein-Hawking entropy, but Hawking didn't himself believe it until he reproduced his famous radiation formula. And this eventually led to the formulation of holographic principle by 2 and Susskind, and the logic was roughly like this, that suppose you take this room and you throw in, you try to increase an amount of matter in this room, then all this matter will eventually collapse and form a black hole, and the black hole will have an entropy which is proportional to the area of the room in Planck units, and a quarter of that. So that's the maximal entropy a gravitating system can have, a system with gravity in this room can have. That should be simply the area, the quarter of the area of the event horizon of the black hole that fits the room. And therefore, because the entropy scales like the area and not the volume, it's natural to think that gravity can be rewritten as some degrees of freedom living at the boundary of space-time and not inside. So gravity, space-time should be encoded in some ordinary quantum matter living at the boundary. So that led to the holographic principle, essentially. And until not much happened until that string theory gave an explicit example of such a holographic principle. And so quantum gravity in d plus 1 dimensions can exist in ordinary d-dimensional quantum system, and there's a famous ADS-CFT duality. So you must have seen it in popular science literature and all. So essentially string theory, a precise string theory, type 2b string theory in asymptotically ADS space-time can be mapped to a precise field theory, n is equal to 4 supersymmetric Yang-Mills. And since then, this paper by Maldacena has 17,000 citations. And so because of the holographic principle, it's quite clear the black hole information paradox should have a resolution in principle, because you can write this formation or burning because the black hole maps to a thermal state in the dual field theory, and therefore the black hole evaporation can be mapped to a burning of a coal in the dual field theory. And since we understand how coal is burned from, and there is no problem there to resolve there is no paradox there, so there should be in principle a resolution to black hole information paradox. Now, where is the catch? The catch, of course, is that we cannot do the translation. We do not know how to translate all these degrees of freedom, or this separation of degrees of freedom properly, and convert that into a language of quantum spacetime. So this is something. Nevertheless, string theory holography has accounted for the Bekenstein-Hawking entropy of the black hole, and there's an immense success. And until 2020, we couldn't understand exactly what is going on or how to translate burning of a coal to the evaporation of a black hole. So in 2020, there was remarkable progress, and all of this actually came from very deep work, which tells you how to rewrite holography or understand the holographic principle in terms of quantum information theory. So that is a major and biggest advance that has happened, and so I will spend a lot of time on that subsequently. And recently, this input of quantum information in holography has achieved a breakthrough in understanding the Page curve, but it also has opened up a new knowledge of fantastic unknowns. So previously, which were unknown unknowns, have become known unknowns, and we have recently found a very gold mine. So there are more questions than answers now, and that is quite fascinating. So this is a very fascinating development where we have managed to contribute something, hopefully. So I will come to that. Okay, so that's rather a very quick and bad summary of the black hole information paradoxes. So what I will do now is to go to very basic quantum preliminaries, so that so I just assumed that you know something about basic quantum mechanics in this talk. So you may not know what's a density matrix. So a density matrix is essentially telling you that you may not know the system, the state of the system completely. For a quantum system, you have to tell what is its state. But suppose if you do not know what it is state, you could say that, okay, I know it's an average of certain states. And each state gets some probability weight p, and which lies between 0, 1, 1, and this sums to 1. So it's basically, that's the best you can say about a state. And in some basis, it is this density matrix is an operator that can be diagonalized. And the way you produce this is as follows. So you can say that I have a system and an environment, and I cannot access the environment. I can only measure the system. In that case, you trace over the environment. And when you trace over the environment, you produce such a statistical mixture of pure states. And the expectation value of a measurement would be simply trace of rho times O, and this is it's basically then an average. So you do a measurement in each of the states, and then you take the average value of that. So that gives you the expectation value. So this is essentially a quick summary of what you mean by a density matrix. And the entanglement entropy would simply be a measure of a degree of ignorance. So entanglement entropy is simply this Shannon entropy of a message. And now the quantum version is simply trace rho log rho. So that if I write the rho in this way, then it's easy to see that it will be nothing but some pi log pi. And then we also need this notion of relative entropy. And this is basically the classical version of this something called Kullback-Leibler divergence. So if you have two probability distributions and you want to say whether how well you can distinguish them, and then you come to this notion of the relative entropy. So relative distinguishability is simply trace of rho log rho minus log sigma, and it's simply a property that it is always positive. This thing should be always positive. It's not quite symmetric in terms of rho sigma. But however, the main property is that it will be zero only if these two density matrices are identical. Okay, so now I come to a definition of a quantum channel, and this is what is going to be important. So basically a quantum channel is any physical process. So any physical process will be a unitary evolution, and initially you could think that you have the system and environment are not entangled in some product state of this kind, but it also goes through if it is not the case. So basically the time evolution operator, any physical transformation will be given by unitary operator, and then you trace over the environment. And this basically is known as a general quantum channel. The N stands for noise, but it need not be noise. It can be any arbitrary physical process. So there is a theorem that you could rewrite this in something called the Krauss decomposition. So there exist operators which I call EI, and such that you can rewrite this thing in terms of this channel in terms of the Krauss operators like this. And since the trace of this density matrix has to be preserved because by conservation of probability, so this would simply imply that if you put a trace here, it will simply imply that by cyclicity of trace, then you can easily see if some ei dagger is equal to 1, then trace of this map also, the map preserves the trace. So this is essentially what is called a completely positive and trace preserving map. And the dual Heisenberg picture in which the state do not evolve but the operators evolve would be essentially the reverse of this. So instead of u dagger, you do u dagger u and trace over the environment. But now the similar thing will be different because what you require is that identity operator is preserved. So here the Krauss decomposition would tell you that ei dagger ei is identity instead of ei dagger is identity, and then this is often called a completely positive and unital map. So that's the Heisenberg dual of the picture of the compared to the Schrödinger picture. So now what we say is that whether you can correct some noise channel. So essentially what you are doing is that you are subjecting it to some noise, and some information can get lost because of the tracing over environment. The question is whether there exists some subspace where you could correct this noise. And this is called the principle of correctability. And there are theorems that tell you, which will be important for us when it is possible or necessary and sufficient condition when you can correct or not correct such a noise. So let me first define what you mean by correcting a noise. So correcting the noise would simply mean another quantum channel, which is called the recovery channel. So you basically act it on, so you take, there is some subspace, code subspace, where the code subspace is where information is encoded, where you want to preserve. So you want to pass some message through a quantum channel. So you put the you put your message in this code subspace and not in any subspace. So let us say this is code subspace C, and then what happens, you take some recovery channel, which is R, which is also a completely positive unital map, which acts on an operator X, and then when you look at this recovered operator and the original operator, they will have identical action on any state vector in the code subspace. And whenever such a thing happens, whenever such a thing exists, you say that the recovery map R performs quantum error correction. So this is simply the definition of the recovery map. However, it's important to note that it may not, this relation is only true if psi lies in the code subspace, but not outside of the code subspace. So there's a theorem, and this is a very nice theorem. So you say that this error correction is always possible if the following condition is satisfied. So you take an algebra of operators A, which acts on a code subspace C. And there is a projection operator, projector P, which projects to this code subspace. And this is correctable against a noise channel N if and only if this particular condition is satisfied, is that any operator X, sorry, I forgot to write. Okay, so this X belongs to this algebra. So if X commutes, so X belongs, for any X that belongs to this algebra, commutes with the errors that corresponds to its noise channel N times P, where P is a projector. If this commutation relation is 0, in that case you can correct for, there will always exist a recovery map which can correct for this noise. So this is a particular theorem that is very important, and this will be important for us. So a general paradigm is as follows. So there is some source of information, and then you encode this information into some subspace. This is called the encoding map. E is a quantum channel, and then you transfer this encoded info through a quantum channel, and that gives you a noise map. And then you recover the message by applying a recovery map. So this is a general paradigm that you want to say for quantum communication or quantum information processing. So what I want to tell you is the space-time is also such a thing. The quantum space-time can also be understood as such in the same paradigm, the holographic principle. Okay, so here is what is it. So essentially, when you define an algebra of observables, it's like a von Neumann algebra that you define in something called a causal diamond or something called a domain of dependence. So all these things will become precise. I'm just making an introduction of these ideas here. So for this diamond has something called an entanglement wedge, which is this which is the entire blue, this science-shaped region, science-shaped. This is also like a wedge. So what is happening? And then this is a picture that we have that will become important. So when you take a section of this, this is A, and the rest of this thing, or the boundary, is A bar. So this is where the field theory lives, at the boundary. And this is a bulk spacetime. This is small a that lies within the entanglement wedge. So the idea of the entanglement wedge will become clear, why it is so important in this language of or2 state. So the important development that has come is that the holographic principle has become more precise, and you can say which part of space-time is encoded in which part of the boundary, on which how this algebra working. So essentially this is the idea, the same kind of quantum channel that I talked about now can be understood in this. So here you have a source. The source of information is indeed the local EFT operators in the emergent space-time. So you have this bulk, you have local field theory or local operators that live in the entanglement wedge or even outside of it. This is a source of your information. And then you're encoding this into your dual quantum field theory, which has no gravity in it. This is the n is equal to 4 superangles theory, or just ordinary thing. So basically you are creating some multiverse with some complex, strongly correlated material. So that is where you are encoding it. And then there's a noise map, and this noise map will correspond to deletion of this A bar region, or the complement of this A region. If you are on a spatial slice, you simply delete or you just simply measure only A and not beyond that. Or you just restrict yourself to the algebra observables in this causal diamond. So that's the noise map, and the recovery map is what you want to understand, the space-time reconstruction recovery map. So, and what we want to show or prove that this space-time reconstruction map should exist. So you can reconstruct the operators only in the entanglement wedge EA of A through this recovery map. So this is, so you can reconstruct the space-time, or you can enter the space-time through this thing. So that is the recovery map. The explicit details of it is very unknown. So that will be, if you have seen this recent movie of Dr. Strange creating multiverses, that will be like a quantum spell through which you can enter the multiverse. And but the thing is that the details of the spell is not known, but we can what we can prove is such a spell should exist. And we will prove that the recovery map exists, and the caveat is that it is only approximate, which I would, and it should be cast in the language of von Neumann algebras, which I'm kind of, there are many subtleties which I'm putting under the carpet for the moment, but in the end, those subtleties actually don't matter so much for what I'm going to say. So let's begin to define these quantities and see how they work. So the first thing comes from understanding the first quantum information quantity that tells you how you can enter the multiverse or this emergent spacetime. So firstly, one interesting thing about ADS is that it's warped. So most of the volume is at the boundary. So even the space or new spaces emerging, if you won't really see this because most of the volume is at the boundary. So it will look to you like that you are only so it will not be really visible in that way. But if you have to see this space-time, that is emergence, you have to, for example, you have to see what is a surface in the space-time. It's not that directly measurable. You have to basically understand some how quantum information is shared between different degrees of freedom. So suppose you look at, you restrict yourself to this region R, and what you have to do, you're interested to understand what is the entanglement entropy of this region R. So you trace over the region R bar in a state, and you get a density matrix here. And of course, there are subtleties, but I'm kind of sweeping them under the carpet for the moment. So anyway, so when you do this, it's exactly the entanglement entropy that I defined. And this is equal to it's exactly like a Bekenstein-Hawking formula. So here I put h bar to 1, but I should have put the h bar. Here is exactly the Bekenstein-Hawking formula. But now it's not the area of the event horizon. It's the area of the minimal or extremal surface that is anchored to the boundary of R, and that extends into the bulk. So that is essentially the Ryu-Takayanagi formula, which was generalized to time-dependent space-time by Hubeni, Rangamani, and Takayanagi. So instead of minimal, you will say extremal, because this area could be or need not be a space-like surface, or you have to do, yeah. So that's the reason why. And there's also a constraint that this X has to be homologous to R. Actually, there are more such constraints, but I want to only restrict to this. So this is particularly, so this thing and this, you can homologously deform this minimal surface to this R. Okay, so that is essentially the formula that you have. So this can be captured here in a different diagram. So this formula can be proven using path integrals. That was one of the major breakthroughs by Faulkner and Maldacena. So there is actually a proof of this formula using gravitational path integrals. I'm not going to talk about it. But then there is what plays a very crucial role in understanding black hole information paradoxes is this further development, which is this quantum refinement of this formula, is what happens if you also have quantum matter or quantum fields on top of the classical space-time. So that leads to a new kind of surface, is quantum extremal surface. So that surface is basically extremizes the generalized entropy. And the generalized entropy associated with any surface is simply the Bekenstein-Hawking and the entanglement of the bulk quantum fields that live here. So essentially what you do here is that you have to take the area of this thing and also the entanglement entropy of the fields that are living inside this. You take a slice of so this is like a cartoon of this. So you take the entanglement entropy of the bulk quantum fields that live inside this green region. You trace out about the RB bar, and then so you have to take both this plus the area of the extremal surface, and together you have to extremize this whole quantity, and then the entanglement entropy of the boundary region R would be simply the generalized entropy of this extremal surface. So this is essentially the quantum generalization of this, but this has no proof, unlike the older thing. But then the question is there some good consistency checks of this formula, and which makes it inevitable? So to see that, so see some consistency checks, I would have to make some definitions and go on. But maybe I can pause and see if you have some questions regarding the definition of the Ru-Takayama or this minimal quantum extremal surface and the minimal and this classical version of it.
Program essentially depends on the anti-de Sitter space, right?
There are generalizations of this also to flat space, but I won't be talking so much about it. But this Ru-Takayama actually very easily generalizes. What is not clear about this quantum extremal surfaces? Well, people have also done generalizations of it, and many of the reasons why we believe in this formula should go through even for other holography. Other holographic versions of without anti-de Sitter
But
space.
in principle, our universe or whatever is more likely to be de Sitter.
Yes.
So where will it fit in?
Yeah, so I don't have much to say on that, but yeah, that is hard. I mean, de Sitter holography is hard, flat space holography is also
So
hard.
it might be a consistent theory, but may not have anything to do with our nature. Is it a possible resolution of this thing? Paradox?
I won't put it that way. So what I would say is that these are different types of multiverses or different types of objects which might actually emerge in realistic materials, or they can be useful for realities. But these are not things that exist on sky. These are not the multiverses that exist in the sky, but the same time they could be also important or important to understand reality also. I mean,
it can help. I'm not disputing that. I'm not disputing, but they are at the level of effective field theories. Because at the end of the day, if you're going to apply it to some condensed matter systems, etc., now we are going to put the limits on how far it is applicable. So it's going to be effective field theories where
generations of effective field theories.
So where conventional mechanisms of doing field theory is not completely useful, you have to go beyond that. That I agree. There's no problem with that. But the original questions will still remain. So,
well, I would say as far as black holes are concerned, you can still take many lessons from here and apply them. And many of these aspects like entanglement entropy should generalize. But indeed, I mean, there are good reasons to believe these things hold generally, so I will talk about that. That should generalize.
And also, one more minor remark. You also mentioned that area theorem is verified by that gravitational wave thing. It essentially says it is consistent with that. You can't say it is verified. I mean, you can't say it is verified.
Yeah, so
it's consistent. Yeah, it is expected to be consistent. It's consistent.
Yeah, so
okay.
That is how we always say verification in physics.
No. It's more than that.
Yeah.
Okay,
so let me go back to these definitions, and so here I am drawing a causal diamond or some kind of a diamond here. It's called domain of dependence and also known as causal diamond. And this is essentially the set of events which are necessarily influenced by A or cause A. So here, if you look into this upper region, these are the events which are necessarily influenced by A. Because if you take a point here and draw its backward light cone, the backward light cone completely will be inside this region or will intersect A. And similarly, but if you take somewhere here, its backward light cone will intersect part of A and partly complement of A. So you have to be inside this triangle. And similarly, you can say about what will cause A. You can make a similar statement. You can also, there's another way to say this. You can take any inextendable time-like geodesic in this diamond. You will necessarily cross A. So there's many ways to define these things. So essentially, it's kind of a causal. In quantum field theory, you often talk of algebra observables that live on this causal diamond dA. And the causal wedge is simply the intersection of the causal past and causal future of this diamond. So if you look into the causal past, it will go like this, and look at the causal future, it will go like this, and you take the intersection, that gives you some wedge, and it is bounded. The edge of the wedge is something called the causal surface, which I call CA, and this is the causal surface. The entanglement wedge is simply the bulk domain of dependence of the quantum extremal surface or the extremal surface, and then you take any Cauchy slice, any space-like size that connects these and this, it doesn't matter which one you choose, and you draw its causal domain of dependence. So basically that gives you the entanglement wedge. So essentially these are the definitions and of these objects. So the first check, one interesting check, is that the entanglement entropy is actually determined by the diamond dA and not by the precise A. So for example, you can deform this surface A without changing this diamond, but the entanglement, but this particular surface, this quantum extremal surface, will not change, and therefore the entanglement entropy does not change. So that's a very important remark. So even the causal surface will not change as long as you keep this dA. And this is sort of consistent with the way we understand quantum entanglement in quantum field theory. So it's basically entanglement should be thought of as a property of the algebra of observables that live here. And what, depending on which state that you're looking at. And so so essentially one way to say it is that the degree of ignorance that you have about the state restricting yourself to the algebra observables in the causal diamond. So that's essentially a kind of Tomita-Takesaki theory. Of course, you cannot actually define the entanglement entropy in a field theory. What you can actually do is define something called relative entropy and take a first law of variation of relative entropy to define entanglement entropy as a proxy. So I don't want to go through all the details of this, but it is sort of the way you think about in quantum field theory as well. Then the next is very important, that if you have entanglement entropy of three such systems, subsystem A, B, and C, it satisfies some inequality of this kind, that the entanglement entropy of A plus B and B plus C should be greater than or equal to this. And this is something that you can geometrically see. So if you just look into the root Takanagi, or the original, just without the quantum extremal surface, the usual root Takanagi surface, then this is very easy to see pictorially. And so this is, so if you look at SA plus B, it will be the minimal surface like this, because if you take the A plus B region, the orange one is the minimal surface, and the blue one is similarly the minimal surface for B plus C. So now you can do a little bit of engineering, or just shift the labels. So think of this as a minimal, this is not a minimal surface for B, but think as if it was. And A plus C would be like this, only the blue one. But actual minimal surfaces are this, right? So by definition, this has to be greater than or equal to this. So that's how you can see pictorially the proof of this formula. But the actual proof in quantum mechanics is actually a huge, several pages long, whereas here you could see it geometrically rather simply. And you can also generalize this to quantum extremal surface. All that you need to do is to assume that matter inside satisfies some good conditions.
It's addition, right? Not equal.
Sorry?
First, the two diagram, that's the addition, right?
I don't understand the question.
The first and second.
No, it's not addition, it's equal to.
Equal, yeah.
No, it's not addition.
Okay.
It is simply, so S A plus B is the orange surface, S B plus C is the blue surface. I simply redrew it so that you can compare this with this. I just shifted the color labels.
Okay. Thank you.
Okay, so then it comes the entanglement wedge reconstruction hypothesis, and this is one of the things that any operator that lives in the entanglement wedge in the cyan region should be reconstructed at least approximately, not exactly, only to a very good approximation, exponentially good approximation in a number of degrees of freedom in this set of observables and on this A. So the question is, okay, I believe this root Takanagi formula, I believe all this quantum generalization, the Engelhardt well, but why should I believe this? Why should I believe this? And this is something that I want to go through. So one of the important properties is that, as I see already in the diagram that I drew before, that the causal surface is always inside, or the extremal surface is always deeper in the bulk compared to the causal surface. So this is one of the most important things that you can also show for quantum extremal surface. So therefore is a good reason to believe in this generalization. And this has to do with the monotonicity properties of generalized entropy. And so I don't want to go through too much details of that. So it is basically very classic GR of the style of Penrose and all, for which he got a Nobel Prize, and which has been continued by Wald and Wald sort of followed those kind of ideas and was able to show that this is always true. And so that's one of the reasons, one of the main reasons why Engelhardt-Wald formula became believable, that this is a natural quantum generalization of the Ru-Takayama. So, but what I want to show, suppose it was not the case, suppose opposite was the case, we would have really a problem in entanglement. We couldn't have believed this hypothesis. The reason for this is that R and R bar is space-like separated. So by microcausality, two operators that are space-like separated will always commute. So now what happens, suppose the opposite was true, that the causal surface was deeper than the extremal surface. So it would mean that you could send signals from R, because it's a causal surface, you will be able to causally send signals from R to the entanglement wedge of R bar. So the operators that lies inside these two surfaces would not commute with operators in R. However, you will be able to reconstruct all operators in R bar, all operators in this entanglement wedge as operators in R bar. But R bar and R commute. So that leads to a contradiction with microcausality. So it better be true that this statement is better be true. So you protect it. Then there's also another thing, that unitary transformations leave the entanglement entropy unchanged. So any unitary transformation that you do, any physical transformation that you do, would only affect the causal wedge, not the entanglement, nothing beyond the causal wedge. And there, since you only affect this part, the extremal surface which lies outside this causal wedge should not be affected. And therefore the entanglement entropy remains invariant under unitary transformations, which is the simple quantum mechanical result that you should have. So because of these reasons, but all these properties follow from very deep GR, okay? So it's a very non-trivial thing that in GR that you have to do to show that this is true. But now what I want to show is that there is a very nice formula that comes up, and this is called the Jeffreys, Lukowitz, Maldacena-Shue. It's often called JLMS formula. So it will take some time to go through it. So this is one of the basic reasons that leads to this entanglement wedge hypothesis historically. One thing is important, that there's often important to define something called the modular Hamiltonian, so which is simply log of the density matrix. It might look like a funny definition, but essentially what it is, we'll see why this is an important thing. So you look at the entanglement entropy of a region A, that is simply the expectation value of minus log rho. So you can simply think of it as expectation value of the modular Hamiltonian. So now you can rewrite the relative entropy, which I defined earlier, in this way. So you can define it as, instead of writing this, you can add and subtract the sigma log sigma. But this first term is nothing but the change in the entanglement entropy between sigma and rho. So that is minus delta S. So that's simply the change in the entanglement entropy with the minus sign. And this is simply the change in the expectation value of H sigma if you measure in sigma versus measure in rho. So this is we can rewrite the entanglement or relative entropy as a change as a change difference of the entanglement entropy and difference of the expectation value of the modular Hamiltonian. So this is simply a trick for the moment. However, if you believe in this formula, the formula for the entanglement entropy, the formula for the Engelhardt-Wald, so you would say that the entanglement entropy of the density matrix here is equal to the area of the extremal surface plus the entanglement of the bulk fields in this A region, this entanglement wedge, or the fields living here. So now if you take a log here, so basically it means that you can promote this area to an area operator who's, so that's actually the way to think about in quantum gravity, area should be an area operator, and you take the expectation value in the bulk density matrix. And then it implies that the modular Hamiltonian in the boundary is equal to the modular Hamiltonian of the bulk quantum fields, HA plus the area. Okay, so that simply follows from the Engelhardt-Worm formula. So now what you can do, you can simply do this trick that you can go back to the result and say that if you can look at S rho A sigma A as minus delta S plus this, the formula I wrote. But however, delta S by the Engelhardt-Worm formula should be then the change in the area plus change in the bulk entropy. And similarly, the change here should be equal to change in the area plus change in the modular Hamiltonian of this of these things because we already already derived this from here. So now if I do this addition of delta S and this thing, this area term cancels out, and remarkably you get that S rho A sigma A should be minus S delta A plus this thing, and then you get that the relative entropies at the boundary and bulk are exactly equal. So basically this is tells you that, so this implies that you should be able to reconstruct everything here through here. So that sort of led to the historically the interpretation that you should be able to reconstruct things in the entanglement wedge in the dual theory. But this can be actually led to a statement and a proof later. So suppose you have the field theory Hilbert space, which can split into A and the complement, and the code subspace where you are encoding the information of the bulk fields has also a similar split, which is HA and HA bar, the complement, and this is a subspace of this full Hilbert space. And then you take at any operator O that acts on this particular A. So now you can define density matrices very easily, both in the bulk and boundary, and which are this simply, you simply trace out either capital A or capital A bar, or you trace out small a. So you can do either of them, and you can come or define rho A bar, sigma A bar, rho A bar, sigma A bar. And because we derived this formula, the JLMS formula, that the bulk and boundary relative entropy are equal, and we know that this will be 0 only when these two are the same density matrix. So essentially, the JLMS formula also implies that rho A bar is equal to sigma A bar would imply these students. Rho A bar is also equal to this. So although this is a subspace of this full Hilbert space, this statement of equality will imply each other. Sorry? I can't hear. Okay. All right. So the theorem is that if this, there has to exist an operator OA which acts on HA. So you can reconstruct any operator O that acts only on HA through an operator OA that acts only on HA as far as the code subspace is concerned, where the code subspace is the code subspace here. Of course, outside this code subspace this need not be true, but inside the code subspace, where the code subspace is simply the subspace where this particular semi-classical geometry is true. Okay, you can think in that way. There could be many semi-classical geometries that fill in the bulk, which are exponentially small corrections. But at least in this particular space-time, this is basically a subspace of the full Hilbert space. So on this code subspace has to be true. So basically now I can easily prove this. So this is a statement, this is a proof of the entanglement wedge reconstruction. The proof is that suppose you take a state psi that belongs to this code subspace, and you do an unitary transformation with lambda, and O is something that acts only on the HA. So O is an operator which we already assumed that acts only on this Hilbert space of HA. So when you do this, so basically so this is something that unitary transformation, you generate something psi. Now, since psi and phi are related by unitary transformations that have only support in, it should be small a, not capital A. I'm sorry for that, as a mistake. So that implies that the rho A bar has to be equal to sigma A bar. So that implies this. So because on this part it acts like an identity. So if you trace out this, it has no effect, and therefore these two things are the same here. So essentially, it will lead to this. It's very easy to show this. So now we said that if rho a bar is equal to sigma a bar, it will imply that rho a bar is equal to sigma a bar in the big space, in the full Hilbert space H. So that was the implication of the JLMS formula, that although it's a Coates subspace, the tracing over a bar and the tracing over capital A bar will have the same effect. Then we could say that, so that's the implication of JLMS, and so that is what we get. And therefore, any operator XA bar that acts on HA bar will have this will have the same expectation value on psi and phi, because if these two are identical as far as, so if these two density matrices are identical as far as capital A bar is concerned, it means that if you make measurements only in A bar, then you will not be able to distinguish these two states. So basically, these two states will be indistinguishable. But however, psi was e to the power I lambda O times phi was this, so it will imply psi will be equal to this unitary transformation of XA bar. Now you simply expand in lambda. If you expand in lambda, you get that XA bar will commute with this operator. And this is exactly the condition that the theorem that I said before, that you should have this, if this is satisfied, if for any operator this is satisfied, there should exist a recovery map. So that was the theorem that I stated earlier. So basically, XA bar, so any error, the error that we are, so noise channel that we are now looking at is deletion or tracing over this A bar. So over this erasure channel, so any Krauss operator, showing that any Krauss operator will commute is equivalent to saying that XA bar and O will commute. So therefore, if it is true for all psi's in this Coates subspace, we have this condition of recoverability satisfied, and the claimed operator OA must exist. So this is how you prove that there should be entanglement wedge reconstruction. Okay, maybe for interest of time I shift it, but essentially then we could also ask what exactly is a recovery map, and the hypothesis is that it is related to the modular flow.
Excuse me, that previous theorem, there exists that OA, right? Can you go to that statement?
Yeah?
That statement, not proof, just a statement before, yeah. Mm-hmm. So there exists OA acting on XA, right? Which reconstruct O or something. So that exists unique on some Coates space. There exists some Coates space such that OA is unique, or?
Well, the Coates space does exist by assumption. So, or
some specific Coates space that is unique or something.
Is it unique? The Coates space I already. Well, the Coates space would be the space. I don't understand what the question. So the Coates space is simply the space where you have a particular geometry that fills the boundary. So that could be that you can understand as a Coates subspace of the full Hilbert space HA, and that you can understand by using just simply extending, or just by doing usual kind of perturbation theory, or on this space-time, you can actually understand how this map actually. So this particular recovery map actually can be explicitly constructed on simple cases. Yeah.
Okay. So uniqueness not it shows existence.
Yeah. So far it only should exist, and in fact uniqueness is not even needed or necessary for anything that follows. Yeah.
Okay. Thank you.
Okay. So basically the idea is that you should take operators here. You have to do something called a modular flow, which is defined as the flow through this modular Hamiltonian in order to enter the bulk. So I don't want to go through this, and this is something similar to.
Sorry to interrupt again. Sorry,
yeah.
I'm really sorry. So my point is, it's like I was wondering if it is possible. So you have an extremal surface, so you have some information contained into it. So there is any chance that your information can get scrambled outside of your extremal surface and it can go to the A bar or something like that over the time?
I also don't understand. What do you mean by scramble outside?
I mean, information can get outside of this region. You said we can recover everything if we are within the extremal surface, right?
Oh, well, okay. So if you take a point here, right? it can be in the entanglement wedge of many different boundary regions, okay?
Right.
So because if you take two things, so that this operator has, so that's related to the question, this operator need not have a unique reconstruction. It can be same operator in the bulk, can be reconstructed in many ways in different boundaries of regions. So that's certainly, and this is the whole point of quantum error correction, that you build in this redundancy so that you can correct.
No, but that is the point of noisy challenge. I can understand the recovery map. Probably we'll talk about page recovery map. So that is related to the noisy channel. I'm talking about even the unitary in a correlated system, in a strongly correlated system, information can get scrambled in different parts.
I think you're confusing maybe two different. Okay, I will talk about scrambling later, but this has nothing to do with scrambling. It's simply a statement about whether such a recovery.
I was just wondering there is a possibility or not. I was saying.
Well,
so
in a way, I don't know
possible.
what you're exactly asking, but one particular operator here can have multiple reconstructions at multiple different boundaries, and these two will be different reconstructions. So in a way, you could say so there is some redundancy. That's what you mean by probably scrambling. So the encoding of a point in space-time is encoded in a very redundant way in the dual field theory, and that's exactly what you need for error correction to be possible.
I'll talk about it later. Yeah.
Okay.
Thanks.
Okay, so now we come to black holes, and here I would be faster. So the Page's formulation of Hawking's formulation loss paradox can be resolved by a refinement of the entanglement wedge reconstruction hypothesis. So what was wrong about the Hawking computation was not the Hawking computation of the effective field theory outside the horizon, but it was that was correct. You can actually trust the semi-classical spacetime and all that. But what went wrong is the way he computed the entanglement entropy. So the statement is that if you connect some system to a system that gravitates, some system that is non-gravitational quantum system, to some system that gravitates, you have to revise the rule for computing entanglement entropy. But that rule is not something that is derived from or rederive. It's not something that you bring out of the hat, but simply a consequence of the usual Engelhardt-Wall and the Ruther-Carnegie formula. Okay? So let me convince you about it. So it's a rather simple consequence of it. Okay, so that's how it works. So suppose you have evaporating black hole at very early time, this is very late time. At very early time, when there's not too much radiation, then you can show that you can reconstruct this. This radiation or the whole green region can be reconstructed in this quantum dot. Or here, or it's a dual system, and here the dual system is connected to some bath. So that's a holographic picture. So this B system is what is holographic, and this R system is a bath that simply collects the Hawking quanta or whatever evaporates from the bath. So that's a the kind of key or toy model. And many such toy models have been computed, starting with Pennington and several people. And in all the cases, the common thing is as follows, that when there's too much radiation, after page time, there's a lot of radiation here, then there is a quantum extremal surface that emerges here, which you can compute, which you can explicitly compute. And this quantum extremal surface actually, which means that it has an entanglement wedge, which is called the island. So operators that live here should be thought of as the entanglement wedge of not the original holographic system, but this bath R that collects the Hawking quanta. So it's basically the entanglement wedge of this red region. This is the causal diamond where you should reconstruct operators of the island. So this is essentially the point, so let me show you why it should be true. So the most non-trivial thing is the emergence of the quantum extremal surface. So essentially what happens is that at very early time, the quantum extremal surface is very close to the original horizon. But then at late time, so basically you have the Page curve behavior that the black hole horizon reduces, so the entanglement entropy reduces, and the entanglement entropy radiation increases, so all these things are true. But then after the Page time, this particular new quantum extremal surface emerges, and in all these models, which you can show from explicit computations, and this is sort of something like a secular behavior, and then you should be able to make this statement. So another way to put it is as follows. So you have these two intervals, and then you have these two red regions. And in the so what happens is you have this black hole in the bulk, and these are two Hawking quanta. So these two, so this green is entangled with this green, this blue is entangled with this blue. So initially, what happens? This kind of so you have something that flows inside, something that goes here, and stuff like that. But you see that each of these intervals collect only one of the Hawking quanta, and there is more and more of radiation. So because there's more and more of radiation, you get more and more pairs, but only half pairs are collected in the red. So one of the pairs is not collected on the red. So this is simply a time translation of this red interval. So only one or half of the pairs, but as you produce with time, you produce more and more such pairs. So the entanglement entropy of the red intervals is going to increase because it collects more and more quanta, but only half of them. However, at very, very late time, this island emerges. So as a result, what happens is as follows. So you have to compute the entanglement entropy in a different way, and you have to also include the island. But the island will collect both the pairs. And because it collects both the pairs, eventually the entanglement entropy is going to go down because you see both the pairs, so it's a pure state. So you have no more ignorance, and it goes down. Okay, I have 5 minutes. So this allows this new kind of rule called the island rule to emerge. And the island rule is as follows, that essentially it is a consequence of unitarity and this thing. The island rule simply tells you that that you have to first take all possible I. So I is this particular region, this interval capital I that we have said is island, this is capital I. And you have to take all such capital I's and take the union of R union I and compute the bulk entanglement entropy in this thing and take the area of the extremal surface that bounds these islands. Right? So basically that is the island rule, and you have to take all such, so you have to extremize over the island, and then if there are many such islands, you should take the minimum value. So basically that is the island rule that you have to apply, but this is not actually a new rule. Why? Because if you believe in the quantum extremal surface formula, then this rule will apply to here, to the original entanglement wedge of this of this thing. So there you can apply the usual Engelhardt wall formula. But then you can also see that the full state of the radiation, and if you look at the full Cauchy surface, which includes the island, then this particular interval and also this interval outside, so it's a pure quantum state. So the entanglement entropy of this times this will be equal to the entanglement entropy of this particular green interval, because it's a pure state, then S entanglement entropy of some region is the same as that of the complement. So if you have unitary evolution, then the entanglement, then the actual formula that you have for the usual Engelhardt wall prescription would automatically imply this this island formula. So it's not something new rule that you're creating from hand, but simply a rewriting. So it means that if you couple a non-gravitating system with a system that gravitates, you have to change the rule for quantum computation of entanglement entropy. And just like the original Ru-Takayama formula can be derived from gravitational path integrals, you can also derive this properly using this. The whole thing, what happens is as follows, that you have new kinds of maybe I can skip this. So essentially what it means that you have this the important thing is as follows, that this original space-time knows about the entanglement entropy and the Renyi entropies of the Hawking radiation, but it doesn't tell you, we do not yet know how the information is coming out, but we can compute exactly the rate at which it comes out and the details of the information, many other details of the information. So, and then you can say that this bulk local operators in the island can be reconstructed via operators in R. So that is a very important thing, that is simply a rehash of the proof of the Dong, Harlow and Wall, which I showed earlier. You can just rerun the same proof and show this statement to be true. There is also a subtlety that comes about, is the state dependence. So this is somewhat different if you have a black hole versus not a black hole. So what happens is as follows: if you take a very large region in the boundary, you will have the same thing, but in principle you can have two extremal surfaces, A and A and capital A2 and capital A1. So first of all, you have to satisfy the homology constraint. So typically A2 is greater than A1. So in reality, you should choose A1 and not A2, right? Because A2 is greater than A1. However, you have to satisfy the homology constraint. So A2 has to be homologous to A, so you have to choose A2 and not A1. So that's the thing. And then if there was just the usual geometry, then you have to simply choose this. But suppose you are in a black hole microstate, which has no horizon or anything, then you don't need to satisfy homology constraint, then A1 should be the right choice. So if you look at a code subspace that has enough bulk entanglement entropy to offset this with this, you have to have so basically, what you have to do, the code subspace so the reconstruction of the operators in this A prime region would only depend on the choice of the code subspace, but not on details of the state in the code subspace. So it will be state dependent, but actually what it means is code subspace dependent. So you just look at the maximally entangled state in this code subspace, and there you will be able to, so if you look at, so A2 can change to A1. So this particular operators, which lies A prime, the reconstruction would be state dependent and exponentially complex. And there's a very good reasons to believe why this should be true. And if you believe in this, then many other paradoxes can be resolved. The so-called AMPS paradoxes and all, which I haven't yet got time to talk about. So basically, the state dependence can be also put in the language of quantum recovery, subsystem recovery quantum channel. And so there has been many versions of state dependence. I mean, I should certainly say that Subrat Raju and Papadodimas were the first persons to bring this into account. But this is a version of state dependence which can be grounded in quantum mechanics in a very rigorous way, and is consistent with all the ways we understand how holographic principles should be understood in terms of quantum information theory. So basically, I kind of end the talk, but I didn't get time to talk about other things, but that's fine. I just want to highlight certain things that Shantan, can I get 5 more minutes? No, sorry. Okay, then I can. Okay, 2. Okay, all right. So I just then make a brief summary of these things. But there are many paradoxes about how we actually encode quantum information in the Hawking radiation. So that is not very well understood, and I think the way to go forward is actually to construct microstate models. So one of the many important things that people have pointed out, that if you think about these kind of toy experiments, that you should also have something called information mirroring. That if you throw some diary into a quantum black hole or a black hole, the information immediately comes out from the black hole. You can immediately read out from the Hawking quanta. However, the information about the black hole interior would be exponentially complex in the black hole entropy, and only then you can resolve many paradoxes. So we have created some microstate models that actually allow such understanding, and it turns out such microstate models have very, very important, or can say something also about strange metals and all, but I couldn't go much into it, but I was happy just to review the importance of this subject. And so I just want to point out that actually the black hole microstates actually give you some very interesting approach to also effective field theory. So what happens is as follows: the way you kind of see a complex black hole microstate, or to understand a complex encoding, would be as follows. So let me give you a model, and just give me just 1 minute, I will just summarize. So basically you can think some kind of microstate models that we were able to construct that satisfies or resolves all paradoxes of the encoding are as follows. They are basically collection of some small quantum dots which are represented by these 2-dimensional throats of black holes. So the horizon is basically fragmented spacetime. So horizon is not, so you can think of the horizon as some kind of lattice of quantum dots, and each of these quantum dots create an emergent 2D black hole or 2D spacetime. So it's a fragmentation of spacetime. And then what happens is that if you incorporate Hawking radiation here, it turns out that the throats behave as if they're independent of each other. So it means that the throats behave as if they're decoupled from each other, and they try to behave in independent ways. And that leads to saturation of this strong subadditivity of entanglement entropy and resolves many paradoxes like the AMPS paradox. And but this is something called conditional decoupling. So what it means is as follows: they are not really decoupled. They act as if they are decoupled, but the parameters are sort of mutually agreed. So the parameters here should be agreed by the parameters of the other. So you cannot just independently choose your parameters. And that leads to a very new way of understanding effective field theory. Because in such microstates, there can be enormous different scales in the problem, that each throat can have an enormously different range of masses. And however, still, if you look at, and this is how we apply to strange metals, we try to apply such ideas to strange metals. And what the consequence of it is that although if you're looking at a particular observable, still, we can show that only a few subset of degrees of freedom contribute to the observable due to this conditional decoupling. So the other degrees of freedom are merely spectators. They don't really play an active role. They simply play a spectator role by being conditioned by this particular other observables. But to capture the dynamics of capture how a particular observable is measured, you only need a few degrees of freedom, a few effective degrees of freedom. So that's a completely new way to understand effective field theory. So that's why I think understanding black hole microstates are very, very important for theoretical physics. It can lead to creation of very, very new paradigms that can help us to even understand many complex systems and create new kind of effective theories with inputs from quantum information theory. Okay, so sorry for going a little over time. So here is the end of my talk.
Thank you very much, Ayan, for this very nice talk. Please, any questions?
Yeah, should we expect the page transition, that page curve, to be a sharp transition at the page time?
Oh, very good question. No, I mean, if you in these models, if you are doing just classical computations that is based on a classical space-time and only not incorporating, perturbative non-perturbative effects, then this should be a sharp transition, but otherwise it should be a fuzzy. It should not be very, very sharp time that you could define.
Okay. And at one point, while proving the JLMS relations, you showed that like the Hilbert space factorizes, but that is not very a rigorous thing, right? In local quantum field theories, yes, you cannot really factorize.
Yes. So all of these statements which I made. So this actually I should have written it. So if you read our review, we have cited papers. Mm-hmm. So Monica and there were this papers by some ENS people who actually cast all of that in the language of von Neumann algebras. And you are right that it should only be thought of as an approximate recovery and not exact recovery. But all of these subtleties can be taken care of using the usual properties of von Neumann algebra. So, but that makes that it more bulky. So whenever those things work out, we don't need to test. People don't usually talk about the subtleties. That's sort of the standard.
One last question. So what we are trying to do is employ quantum information ideas or quantum information models as such, which actually deal with finite systems, right? Whatever models we can build for that, those are finite systems, whatever models we have. But when we come to black holes or when we come to QFTs in general, we are dealing with infinite degrees of freedom, and there could be something very like emergent properties could appear there. So how well are we in model building? How well are we doing using quantum information models?
Well, I mean, many things go through, many things do not. So, for example, what are the things that go through? Like these kind of general properties, general things statements that I made about, like entanglement, reconstruction, all this thing will go through. But what will not go through if you just simply try to make a model of holography using simple tensor networks? That completely fails. So, for example, tensor network models are able to reproduce this Ru-Takagi surface, but they are not able to reproduce Renyi entropies. So there are many subtleties like that can happen. So tensor network models could only have limited. So you should be careful. But sometimes many abstract statements actually generalize to infinite dimensional cases. I mean, of course, one has to check whether there is no. So one has to go to a maths department or take help of mathematicians to check that whether it goes through or not. But so then you can sweep it under the carpet. But you are also right that sometimes you can see many new emergent properties that are only possible for this. For example, there's a recent paper by Hong Liu talking about how times emerge in von Neumann algebra. That's only true for type 3 von Neumann algebras. That has no finite dimensional analog. That this. So there are many things that depend actually on this so there are new things that can also emerge. So I think as physicists we should try to learn language of von Neumann algebra is very important, and that can also have implications for real like strange metals. Who knows? So I think that indeed one should actually learn the von Neumann algebras and see if something new that we are missing out. You're right.
There's a question.
See, all the things you mentioned about von Neumann algebras are true only for the type 1, type 2 kind of things. Now the quantum field theories are described by algebras which are coming from type 3. Okay, so all these things will have serious difficulties when you want to go to at that level. Okay, that is my concern also.
Yeah.
Okay. Now the second point is we have something called time in our space-time, which in principle under diffeomorphism we can't even define what is time also. But there is a time which is coming from algebra, which is coming from that modular this thing, which is modular time, which is related to the transformations you can do with that, etc., which is defined by some kind of positive definite operator, which tells you it always increases. Okay. Now, I do not have a clear idea of how these things can be mapped within this framework which you have. Okay, it is not even clear. But in principle, the difference between whatever you have infinite and the finite systems which I can have large number n going to 10 to the power 120. Still it is finite. It is not infinite. So, but for all our measurement issues which we are talking about, most of the time we are only doing finite number of things. We have only finite number of informations as in an operational sense. So how will I really compare and claim that that is the point?
Okay, so yeah.
And lastly, one more thing.
Okay, so otherwise I'll forget all the questions. So let me. Okay, so the first thing I think is similar to the question that was asked. So many of the things like definition of entanglement entropy. So you cannot define density matrices and trace. But however, people are. I mean, there are ways. I mean, there are ways to go around it. For example, you can define something like a relative entropy, which is very well defined in type 3, and then you can define an entanglement entropy through a proxy by some variation with respect to the vacuum. And essentially what happens is that when you do that, the entanglement entropy has a problem of this UV divergence, but that's specific only to vacuum. But I mean, that's the same, sorry. That's the same as in vacuum, as any arbitrary state in vacuum will have the same UV divergence. So when you derive, if you define through the variation of the entanglement, the relative entropy, this divergent piece is automatically gone out, and you see only the state dependent part. So there are ways to, so the state dependent part of the entanglement entropy is well defined, for example. So there are many things go through, actually, all the subtleties people have understood. It's not, so there are people who have worked out all these things have been very much discussed and debated and worked out in terms of von Neumann algebras. So most of the things that I said. Okay, and the second thing that you were asking, what was the second question was about? Again,
because
the finite
time.
Oh, the time. Oh, yes. So, yeah, the time, well, this modular flow is actually, this is something that people are trying to understand. So I think there is some better understanding of the extremal surface itself, how it's related to the modular flow. So there are very beautiful papers by Faulkner and others who have made a lot of progress. And essentially the relation between this recovery map, so there is a way to understand the modular flow in the bulk. And this way is very, very similar to a twilled best map, actually. So a lot of the people are making progress towards that direction. So I don't think it has a fully settled program, but it's one of the exciting programs, yeah.
Yeah, a minor question. See, what you have, since you started with black hole, with the classical notions about black hole, it's a kind of a system which is a one-way street. So you have something like a dissipative system which is described not by a unitary evolution. Okay? But if I want to describe...
Well, I disagree there, because the things that we are talking about are complete unitary evolution. But okay, in some of the models that we have discussed where you have a system connected to a bath or something, but you can also have black hole formation if you have only, so basically what is happening is that the black hole formation is simply an illusion of, so there is a very well-defined subject, like you understand thermalization of isolated quantum systems. Isolated quantum systems, of course, if you do not have unitary evolution, they should not thermalize, but they thermalize from the point of view of simple measurements. Like if you just measure 2-point functions, people have done, for example, 2PI effective field theory methods and shown in ON models that when you simulate using 2PI effective field theory, you do get thermalization. So for example, you get an emergence of the fluctuation dissipation relation of 2-point functions, which defines for your temperature. So this happens. I mean, so if you're doing a very fine-grained measurement, if you're not doing extremely fine-grained measurement, you should exponential. So if you look in a large n limit and you are looking at a simple operator that scales like a polynomial of n or something at max and not exponentially with n, you do see thermalization, and that is what is captured by the bulk geometry.
Yeah, but the real problem which as information paradox issue as posed by that is using only semi-classical gravity by Hawking. Now, in some sense, kind of a dissipative system, if I want to make it unitary, I can double it or one more system, which is the bath, from where heat is going from one to another, and it will be unitary in the total full system. Okay. Now, what you are trying to say looks similar to that you have not only this thing, but you have to have the boundary, the dynamics of the boundary also to be included.
Not really, actually. I mean, you should be able to pose this problem even without a bath. But the problem with ADS safety is that the usual Dirichlet boundary conditions that you put in prevents black hole evaporation. But you can think, but still, I mean, if you go to the large n limit, the black hole is not really is a fuzzy object, and you should be able to understand.
In some sense, black hole will never be formed as a formation of the black hole issue.
Yeah, so
the
true.
Ideal black hole.
Of course, the quantum black hole is not really a black hole. Yeah.
Ideal black hole may never be formed, but for our time scales, it's as good as a black hole which we consider, right?
Yeah. The question is, why do we see a classical black hole at the first place, right? This is one of the major questions.
As an approximation.
As an approximation.
Yeah.
So basically, one way of putting it, which I didn't get time, is to ask why there is a black hole complementarity that sort of emerges in operationally. So that is, of course, the question. That's a very deep question. That's the whole program is about, to understand that. But the question is to understand it. So although in principle you can see it in the dual language, you have to convert that back into the space-time language. So you have to say, you have to make some approximate separation of degrees of freedom, like what is interior, what is exterior. So then the paradox emerges in operational sense. In reality, there is no paradox, of course.
Okay.